In this video, we're talking about inverses of functions, okay? So, by the definition of a logarithm, you should have seen by now, or at least guessed, that the function g of x equals log base b of x is the inverse of the exponential function f of x equals b of x. So what that means is exponentials and logs cancel each other out, which we've already seen that before in an earlier chapter when we were solving exponential and log equations. It's because the reason why that works out is because their functions are inverses of each other. This means that since the functions are inverses of each other, that the graphs of these two functions are reflections of one another across the line y equals x. And that's true for any two functions that are inverses of each other. If you have two functions that are inverses of each other, they're always going to be reflections of each other across the line y equals x. The line y equals x is represented in these pictures as a dotted line. An inverse relation, we talked about relations at the very beginning of this chapter, so now we're talking about inverse relation, and that maps the outputs back onto the original input values. Again, outputs typically we represent with y's, inputs we represent with x's. All this means is that the domain of the inverse function is the range of the original relation. Also, the range of the inverse relation is the domain of the original relation. Seems like a mouthful. They're kind of similar, so it's hard to digest the words. So let's look at the picture. So if we have the original relation and we want to get the inverse relation, essentially what we're doing is the domain becomes the range for our inverse, and the original range now becomes our domain. We're just essentially switching our x and y's. That's what it boils down to. To find the inverse of a relation that's given by equation in x and y, all we need to do, again, switch x and y if possible. Sometimes it's going to be very easy, sometimes difficult, and then sometimes it's not going to be possible at all. So in example 25, we're going to do an easier one. We want to find an equation for the inverse of the relation y equals 2x minus 4. Well, since we're talking about the inverse, I want to first start off by switching x and y. And I mean literally switch them. So everywhere I see a y, I'm going to put an x. And everywhere I see an x, I'm going to put a y. Now I want to get y by itself. So I have plus 4. Cancel out. So I have x plus 4 equals 2y. And now I want to get y by itself, so I'm going to divide by 2. Now, there's more than one thing on top of my fraction, so I have to put it in parentheses. If you don't, it's going to come out wrong. Be sure you remember that for parentheses. So my function is going to be y equals x plus 4 divided by 2. Do not forget the parentheses. And this is the inverse. This is the inverse of our original relation, y equals 2x minus 4. We could actually see that this is a relation by graphing. So what I'm going to do is go to my graph. I'm going to graph the original relation in y1, so y equals 2x minus 4. And now I'm going to graph my inverse relation in y2, x plus 4 divided by 2. Don't forget the parentheses, or this will not work. What we should see is that these two graphs are reflections of each other across the line y equals x, but we can see it even better is if we go to the table. Alright, so what should happen is that the x and y values are essentially switching places, are reciprocals of each other. Okay, so the x and y values should flip-flop. Okay, and that's kind of what's happening here. So everything's looking good. So we have the correct inverse function. Alright, so two functions f and g are inverses of one another, provided that when we compose the functions, f of g of x is supposed to be equal to x, and also g composed of f of x is also equal to x. When we have the function g is denoted by f to the negative 1, that's read as f inverse. So if you see this f to the negative 1, we call it f inverse. Now right here, this composition f of g of x and g of f of x, that's something you should have learned in an earlier class. I'm going to do a quick example. But if you need help beyond this quick example, you're going to need to come see me individually, okay? Because again, this is something you should remember from earlier classes. Example 26, we want to verify that f of x and f inverse of x are in fact inverses. Well, since they're inverses, the rule says that we can compose these two, f of g of x, and we're going to get an x when we finish doing that, and g of f of x, and we're going to get x when we finish doing that. Either one should work. So what I'm going to say is, I'm going to call, instead of f inverse, I'm going to call this g of x, just so I can follow this pattern. I'm going to look for f of g of x. Okay, this is called f composed of g of x. What this means is everywhere in my f function that I see in x, I'm going to plug in because it's in parentheses, I'm going to plug in my g function. So I'm going to start off with my f function, but everywhere I see an x, I'm going to draw the parentheses that represent a place I need to plug in. So I have 2x minus 4. Now my g function gets plugged in. So it's f of g of x. So here's where g of x gets plugged in. So 1/2 x plus 2. Now I just want to clean it up as much as possible. I have distributive property. So 2 times 1/2 is 1. So I have 1x plus 4. And then minus 4 on the outside just falls down. Now keep cleaning it up. 1x is left by itself, and that's just x. Hey, but the rule said f of g of x is supposed to be x, so that means they're inverses. Yes, that works. So yes, inverses. It's really that easy. Again, if you need help with this composition idea, you're going to have to come and see me individually because this is something you should know how to do from earlier classes. In example 27, we have a word problem. Don't freak out. All we're going to do is just read it and then mostly focus on the equation and what the letters represent in that equation. So we know that when calibrating the spring scale, you need to know how far the spring stretches based on given weights. Hooke's law states that the length of a spring stretches is proportional to the weight attached to the spring. And one particular model for one scale is L equals 0.5W plus 3, where L is the total length in inches of the spring, and W is the weight in pounds of the object. We want to find an inverse model for the scale. So let's do part A first. I'm going to do part A in blue. Find the inverse model. So I don't have X and Y this time, I have L and W. So again, to do the inverse, before we said switch X and Y, so this time I'm going to switch L and W. So literally everywhere I see an L, I'm going to put a W, and everywhere I see a W, I'm going to put an L. Alright, so I have W equals 0.5 L plus 3. And now I want to get L by itself, so minus 3. Cancel out, so I have W minus 3 equals 0.5 L. I want to get L by itself, so I'm going to divide by 0.5. No big deal. Cancel out. Now I have more than one thing on top of my fraction, so it must go in parentheses, otherwise it's going to come out wrong. So I have my inverse model as L equals W minus 3 over 0.5. Okay, I can leave it like that if you want to, no big deal. Alright, if you place a melon on the scale and the string stretches to a total length of 5.5 inches, how much does the melon weigh? Well, again, the length is L. We're trying to find weight. So W is what we're solving for. So part B, let's do in green. So we're using this model that we just found in part A. So we're going to plug in what we know. We know the length is now 5.5. W is what we're solving for. It still has to be in parentheses. And now what we can do is either graph or solve by hand. I'm going to graph it. Okay. And again, when we graph, since we only have one variable, instead of W, I'm going to pretend X. Okay, pretend it's an X. So go to Y1 and Y2, clear out anything that's there. Y1, I have 5.5. Y2, I have X minus 3. It has to be in parentheses, divided by 0.5. Graph it. Oh, I already see my point of intersection, so second count, option 5. First curve enter, second curve enter, yes. And I get that X, or in this case, W is 5.75 pounds. So that means that this particular melon weighs 5.57 pounds, which seems about right for a watermelon. Okay, watermelons don't weigh 20, 50 pounds, anything crazy like that. That would be humongous. And that's it for this video on inverse functions. As always, a lot of what we talked about is review, but if you need help with some of the ideas, please make sure you get help from me or a neighbor. That's it.